all. In today's session, let me start our flip-flops, which are JK and T flip-flops. These two are remaining in our all the four types of flip-flops, which are SR, T, and JK and T. So in last class, we learned about your SR as well as your T flip-flop. The drawback in your SR is when S equal to R equal to 1. So there was an invalid state which is occurred in your SR flip-flop. So due to your large inputs as well as your SR external inputs of SR. So both states of your next state is complemented and your uncomplemented states are logical one, which is treated as your forbidden states or the invalid state. In order to avoid that invalid state, for moving to the next flip flop, so using a small modification in the design procedure of your designing of your logical diagram, let me avoid that invalid state in your JK flip flop. It similarly function like your SR flip flop. So we have to treat your J input as your S input and K input as your R input. So J is always equal to S input and K is always equal to the R input. So this shows your block diagram of your JK flip flop, which is having two external inputs along with your for synchronizing your or the controlling your operation of your sequential circuit. We are using the trigger signal, which is the clock signal, and it gives your outputs which are complemented and uncomplemented states. So now JK flip flop truth table as I have given here. First let me learn about. So now we are going to learn about the difference between your SR and JK is due to your JK, J inputs and K inputs invalid state, right? So now here let I apply the J input is equal to 1, K input equal to 1. And a small modification we have done in the logical diagram. So instead of having your two input NAND gates on your first as well as your second NAND gate, let me take here the inputs which are here 3, 1, 2, 3, 4 are the NAND gates. So first NAND gate will have your 3 inputs, second NAND gate is also having your 3. The third input is fed back from your uncomplemented state of your present state, and your third input of your first NAND gate is connected from your complemented state of your present state. Now as here J is 1, K equal to 1. So if I treat J input, your present state is 0, complemented state is equal to 1. So now since this 0 is connected on your second NAND gate input, so as it is transferred, so any input is 0, second NAND gate output become logic 1. If 1 is transferred on your first NAND gate, if all 3 inputs are 1, so clock is 1, J is 1 and your Q and bar is 1. So hence the first NAND gate output will give you 0 output. So immediately upon having your third NAND gate input is 0, your output state of your the next state now it will change from 0 to 1. So and that one is applied as your input of the fourth NAND gate. Hence here the complemented state will now it is transferred from 1 to 0. Unlike this SR flip flop, this JK flip flop now as having here Q is 1, Q bar is all equal to complemented state of your uncomplemented state, which is 1 is now complemented to logical 0. So now your present state is 0, but output is a toggle of your present state. So which is complemented state of your present state. Now let me verify another state, which is your upon assuming your state of your flip flop is 1 and the same input condition which are J, K are equal to logical 1. So if I treat your present state is 1, complementary state will become logical 0. Since here a feedback is provided, so now so this 1 comes as your input. So if all 3 ones are 1s, so the output of your second NAND gate is 0. Next output of your first NAND gate, since of this 0 input which is a complemented output, so first NAND gate output is equal to 1. So if your fourth NAND gate input is 0, so then output of this fourth NAND gate is now shifted to 1. So hence here this 1 is transferred as your input of second input of first NAND gate. So your output of your first NAND gate now it will give you the 0. So present state is 1, next state is a complementary state of the present state, which is equal to 0. So hence here, so we have avoided that forbidden state of your Q is 1 as well as Q bar is 1 with a feedback connection on your JK flip flop. So like this, so we can avoid the you can avoid the invalid state with the toggle state. So when j equal to k equal to 1, we obtain the state is defined as your toggle state since it toggles its present state. So next state is equal to the toggle state of your present state. Now if you assume here the three conditions on your remaining three conditions on your jk flip flop, which are j equal to k equal to 0. So when j equal to 0, k equal to 0, so this first NAND gate and second NAND gate output will generate 1 1. So if you are applying after low input latch with 1 1, so the same steps will be continued as your next step. So hence for 0 0 input, so you have your no change output. So your present state, your next state continues like your present state. So if your j input is 0 and k input is equal to 1, so now so first NAND gate output will give you the logical 1. Second NAND gate output will be dependent on your feedback which comes from your present state. So now if I treat your present state is 0, complemented state become logical 1. So this 0 is applied as your input since clock is 1 and present state is 0. Second NAND gate output will also equal to logical 1. So if it is logical 1, so no change in the state, so 0 is continued as your next state. Next, if present state is 1, so my present state is equal to 1. So then here, so here due to this one input, so the second NAND gate output now it becomes 0. So when it becomes 0, so this 0 input on your fourth NAND gate, so will transfer the complemented state with logic 1, and this one is transferred as your one of the input of your third NAND gate. So hence here, so here 0 is now, earlier it is 0. So since you assumed your present state is 0, so now present state is 1. So complemented state become 0. So here 1 is transferred as your input. So if all the inputs are 1, so second NAND gate output will generate the 0 output. So if it generates the 0 output and fourth NAND gate output will transfer with the logical 1, and this one if I transfer, so 1 is shifted to your 0. If all the two inputs are 1, third NAND gate output become 0. So present state 0, it is continued with the same state. Present state if it is 1, so then it is resetted. So k input is exactly equal to reset input, hence it resets your flip flop or loads the logical 0. Now if j equal to 1 and k equal to 0, what will be our state? So in your SR flip flop, if S is equal to 1, R equal to 0, we obtain the set state. The same manner in your JK flip flop also, we obtain the set state. How we obtain the set state, that we are going to discuss. So J is 1 and K equal to 0. So immediately no need to check for your complemented state of this second NAND gate since one of my input is 0. K is 0, clock is 1. So if k is 0, so I no need to check for the third input. So immediately the second NAND gate output will generate the logical 1 output. But in order to obtain the first NAND gate output, I have to check for my present state. So now present state is 0, complementary state now it become 1. So that complementary state is applied as your input. So hence first NAND gate output, if all three inputs are 1, it will generate a 0 output. So now if any input of your NAND gate is 0, so this third NAND gate output will shift your present state to logical 1. So 1 1, so which will be turned into your 0 state. So hence the set state is obtained when your j input is 1, k input is 0 with the present state assumption of 0. Next, if my j input is 1, k input is 0, along with present state is 1 assumed state and your complemented present state is 0. So this one is transferred as your second NAND gate input. So k is 0, so second NAND gate output always gives you 1. So next if 0 is transferred here, so then the first NAND gate output would also generate. So the first NAND gate output would also generate your logical 1. So if 1 1 are there, so there is no change in the state. So this state is continued as your Exit. So next state. So as here 1. So here 0 is transferred. So hence 1. So 1 1. So here. So set state. So like this. So we are going to have your set state, reset state as well as your no change state in your JK flip flop. Now let me derive your minimal state table of your JK flip flop. So JK and your Q1 plus 1. So if your JK inputs are 0 0, no change in the state. So your present next state is continuing your present state. 0 1 reset state which loads your logical 0. 1 0 is the set state which loads the logic 1. 1 1 is the on your inputs of your JK, which can give you the next state is your complemented state of the present state. So like this JK flip flop will function like your SR and it can avoid the invalid state when JK inputs are 1 1. Next, let me move here T flip flop. How to construct a T flip flop. Before we were moving to the T flip flop, so let me discuss about how to obtain the JK flip flop characteristic equation. So to obtain the characteristic equation of your JK flip flop, we have to write your SSOP expression of your J as well as your Qn plus 1 in terms of your as a function of your JK Qn. So if I write your SSOP expression of Qn plus 1 in terms of your JK, then wherever the functional value is 1, that decimal code we have to place inside the parenthesis. So it is 1 comma 4 comma 5 comma 6. So 1 4 5 6 are my min terms of my Qn plus 1. So now let me map that function onto this. So j of or Qn plus 1 in terms of JK Qn as a function of your present inputs and present state is equal to sigma m of 1 to sigma m of 1456. So now that 1456 I am going to take here as your min terms 1456, and upon mapping your function, so we obtain this using on K-map method. Using your K-map method, a 3-variable K-map we are going to take here. So which can form two groups, two pairs, and these two pairs will generate JQ and bar. First one will generate one pair, which is 4 is paired with your 6 and 1 is paired with your 5. So 1 is paired with a 5 and 4 is paired with a 6. So if 4 and 6 are paired, so then we have your common variables are J row wise, column wise you have your Q and bar. Next, here 1 and 5, 4, sorry 1 and 5 are paired. So here the J is different from these two minterms and the common variables are K and Qn. K value is 0, so hence it is K bar Qn. So Q characteristic equation is Qn plus 1 is equal to J Qn bar plus K bar Qn. Next, from the truth table of your or your state table, we will derive your excitation table of your JK flip flop. So as here JK is so 0 to 0 transition we obtained when J is 0, K is 0 along with J 0 and K equal to 1 in your state table. So from these two cases J is always equal to 0 and K is a don't care. So hence 0 to 0 transition is 0 don't care. Next 0 to 1 transition is obtained when your J input is 0 and K input is equal, J input is 0, sorry, J input is 1, K input is equal to 1 along with a toggle state. So set state which is J is equal to 1 and K equal to 0. So J is always in the two cases it is equal to 1 and K is a don't care. So hence 1 don't care. Next 1 to 0 transition is occurred in a JK flip flop if J is 0 and K equal to 1. In the next case toggle state which where J equal to 1 and K equal to 1. So now by observing these two cases, so K equal to 1 always and J is a don't care, hence it is don't care 1. Next the last case is 1 to 1 transition. In this 1 to 1 transition is obtained when J is 0, no change state and K is 0, or else with set states J is 1 and K equal to 0. So observing that two cases, J is a don't care, K is a value of 0. So hence, so we drawn that excitation table. So using that state table based on your state transition from present state to the next state, and then we found that excitation input required on your JK flip flop. 0 to 0, 0 don't care, 0 to 1, 1 don't care, 1 to 0 don't care, 1, 1 to 1 don't care, 0. Next, let me move to your flip flops. So now a small modification, we were going to do it on your JK flip flop by just connecting JK inputs together and given to a common input terminal, which is your T or your toggle flip flop. Let me name this as a toggle flip flop. So now, so in order to obtain only the toggle state on your JK flip flop, so let me short your JK inputs and given to a common input called as a toggle flip. This is the block diagram of your toggle flip flop along with the clock signal, complemented and complemented state, and logical diagram. So JK flip flop logical diagram only we have taken here. Only the thing is here we have just shorted your JK inputs and connected to the common input terminal, which is your toggle input. So now when T is 0, J and K becomes 0. If J K becomes 0, so present state is continued as your next state. So hence here 0 is the present state, next state is also equal to 0. If my present state is 1, next state is equal to 1. If T is 1, J and K become logical 1, and if my present state is 0, next state is a 1. If my present state is a 1, next state is a 0. So from this truth table, so let me derive the characteristic equation of your T flip-flop. So Qn plus 1 has a two variable function, and that two variables are your present state and your present input. So present state is Qn and then present input is T. So which is equal to sigma m of your 1 comma 2. So now let me take a simple two variable K map, and in this two variable K map let me map your function, so which are your isolated minterms. So hence here T Qn, so Qn plus 1 is equal to Qn plus 1 is equal to an isolated minterm which are treated as your product terms. So T bar Qn plus T Qn bar. So or simply, so it is equal to T exclusive OR of Qn is your characteristic equation of your T flip-flop. Qn plus 1 is equal to T exclusive OR of Qn. So hence here the toggle flip-flops only used to toggle your present state, and that only we were just obtaining as your nexus. T0 no change state, so present state continue, your next state continues like your present state. So no change state we obtain when T0. When T equal to 1 we obtain your toggle state. So here, so I have given your the characteristic equation along with your excitation table. So in excitation table, the transfer of your present state to the next state, 0 to 0, 0 to 1, 1 to 0, 1 to 1 transition is here. So 0 to 0, no change in the state. So T is 0, 0 to 1, toggle input is 1, 1 to 0, there was a complemented state of your present state on your next state. So hence T become 1. So 1 to 1, so 0 is here, 1 to 1, no change in the state. So this is possible when T input is 0. So this is our session today. And in the next class, we are going to learn about your master slave as well as your conversions of your flip flop.